All right, what's going on, guys? Welcome back to another breakdown. Here we go. I'm excited. We got a CP passage breakdown. Okay, this is a breakdown of the section bank passage. Okay, this is a passage from the section bank. Okay, the section bank is known to be harder, so this is great practice. I'm going to show you guys exactly how to make these passages easy. I'm going to show you guys where to highlight, how to not get lost in the details, how to pick the best answer. Okay, not the right answer, but the best answer, because that's what the MCAT looks for. Show you guys how to get them all right. I'm really show you guys how to get all the questions right. Okay, so before I break this down, I want you guys to go ahead and do the passage and do the questions on your own first. Okay, so this is the passage here. Read through it, pause it if you need to. All right, this is the first question. So the 46. Okay, that's the first question, second question, third, fourth, fifth, and the sixth. Okay, this is great practice. That's it, right? Yeah, that's it. Okay, so this is great practice, guys. Write down your answers, see where you went right, see where you went wrong, and learn how to crush the MCAT. Okay, this is how you do it. Hold on, let me sip of my water real quick. Let's begin. A lysozyme is an enzyme that kills gram-positive bacteria by cleaving N-acetylglucosamine oligosaccharides, NAGX. Okay, so I already need to highlight right from the jump. Okay, so what am I going to highlight? I'm going to highlight things that stick out at me. I'm going to highlight things to make a mental note in my head to remind myself about these details in the passage. Okay, also I'm going to highlight what I didn't know before. Okay, I didn't know that lysozyme kills gram-positive bacteria, so I'm going to highlight that. All right, and I didn't know that it cleaves at N-acetylglucosamine oligosaccharides. Okay, so I'm going to highlight that as well. All right. One product, NAG3, has a high affinity for hen egg white lysozyme. Affinity constant NAG3 equals this, delta H equals this, delta G equals this. Okay. When I'm given numbers, I quickly go through it. You don't have to. Don't waste your time trying to internalize these numbers. Okay. The passage will probably ask a question about these numbers anyways, so you can quickly look at it. All right. You don't want to waste your time. Structural studies indicate that NAG3, okay, makes hydrogen bonds with D559, W62, W63, D101, N103, and A107 in a cleft. Okay, remember, these are hydrogen bonds. Okay. In a cleft in HEW lysozyme that is adjacent to the catalytically active D52 and E35 residues. Cool. So we're hydrogen bonding at specific residues that are near these active residues. Okay. Let's keep going. Unlike NAG3, okay, the one we just talked about, NAG monomer interacts weakly with HEW lysozyme, and it is not possible to measure KNAG or delta H of its interaction directly. Oh no, we can't measure KNAG and we can't measure delta H directly. So how are we going to do it? Researchers used competition isothermal titration calorimetry. Okay, I have no idea what the heck that is. I've never seen that before, but do not be scared. Okay, so they used whatever that is to measure the heat of interaction of NAG with HEW lysozyme. So I'm highlighting this. Okay, what do they use it for? They used it to measure the interaction of NAG with HEW. That's what they did. All right. HEW lysozyme, 1 milliliter, 0.1 millimolarity, was titrated with 25 injection of NAG3. Okay, so HEW titrated with NAG3 in the presence of various amounts of NAG, and the heat associated with each injection was measured. All right, they're measuring the heat here through this titration process. Modeling of the heat per injection curves gives the apparent association constant KAP. KAPP is the apparent association constant. All right, here's a figure. We don't look at it. Only when the question asks, we look at the figure. KAPP is mathematically related to the affinity constant of NAG KNAG by equation 1. So this is the equation. All right. By plotting KNAG3 over KAPP versus NAG, okay, the value of KNAG could be determined. Easy. easy, okay? We don't look at the figure and equations only when the question asks for it, okay? So what is this passage telling us? Well, this passage is using some new tool here, CITC, whatever the heck that is, okay? I'm still not really sure what that is, okay? And that's okay. It's okay that I'm not doing backflips and I'm jumping up and down excited that I know exactly what this is and what's going on. It's okay. All right. This part is a little details here that, you know, somebody could get confused with, and that's fine. The question is easy. This question's easy, but the passage is where these details can kind of try to trip you up a little bit. I know that they're trying to trip me up here. I know that. Okay. And I know that other students probably might have gotten a little tripped up here and there, but I know that it's possible. So let's go ahead and answer these questions. According to the passage, what type of bond is cleaved by lysozyme? I told you guys the questions are easy. What bond is cleaved? N-acetylglucosamine oligosaccharides. What's a saccharide? It's a carbohydrate. It's made out of glucose from glycoside bonds. All right, no, yes. Answer is this. I'm confident in my answer choices, so we're going to keep going. What is the approximate value of delta S for binding of NAG3 to HEW at 27 degrees Celsius? They gave us all this information here, all of that. They gave us the delta H, gave us the delta G, they're asking for delta S, and they gave the temperature. All right, you should know which equation we're going to use. We're going to use this boy. Okay, minus T delta S. All right, let's plug it in. Delta G was negative 30 kilojoules equals delta H. Delta H was negative 50 minus the temperature, which was 27. However, you add 273. Okay, this is Kelvin here. So 273 plus 27. Okay, times delta S, and they're looking for the delta S. Okay, this is it. It's all the math you got to do. Simple math, all right? I could do this with... All right, so for this one, I'm going to use a calculator and cheat because I'm pretty sure you guys know how to do the math here. Okay, I don't want to waste your guys' time. So I'm just going to use a calculator and cheat here. All right, if you want me to show you the math, just comment down below. I'll be more than happy to. Okay, I got negative 67. Cool. All right, that's how you do it. We're confident. Let's keep going. Based on the structural studies, when NAG3 interacts with amino acids in HEW, it can hydrogen bond to the side chains of the amino acids at all the positions described except for the amino acid at which position. All right, so here you have the amino acids that it hydrogen bonds with. Okay, that's a messed up question. I don't like that because it literally tells you here that it makes hydrogen bonds with all of these in a cleft in Hu enzyme, in lysozyme. So, and these are all amino acids that are found here. Okay, I don't like that. I don't like this question, but we're going to do it nonetheless. So, 62, we have a tryptophan. Tryptophan, I don't think that it can hydrogen bond. All right, tryptophan, I don't think it can hydrogen bond. So I like this one, but let's keep going. 101, you have, this can definitely hydrogen bond. All right, same thing for the 103, the asparagine. Okay, you're just gonna have this. So you're gonna have carbonyl here and a nitrogen. All right, and this oxygen could go ahead and hydrogen bond. So it's not this one. And then 107, we have an alanine. I don't think alanine can hydrogen bond either. So we're left with 62 and 107. We're left with tryptophan and alanine. Which one cannot hydrogen bond, tryptophan or alanine? The side chains. Which one cannot hydrogen bond, tryptophan or alanine? If I had to choose one, the better answer, I would choose that alanine cannot hydrogen bond. This tryptophan, Okay, when you look at tryptophan's ring and the R structure, okay, it looks like you have nitrogen here. That's why it's very important for you guys to know the actual structures of amino acids, okay? You gotta know them, everything about them. Okay, that's a benzene ring. Okay, I drew it pretty bad, but that's a benzene ring. One, two, three, four. Okay, there should be another one here. All right, I'll fix it. Don't yell at me. Okay. All right. And then you have, it's aromatic, so you have this. Okay, here's tryptophan. I mean, tryptophan does have this nitrogen, and it has this ring. This ring could act like, this ring could have some type of a delocalization of electrons, and this could go ahead and act as a nucleophile. But also this nitrogen here, it could definitely hydrogen bond. Okay, remember, hydrogen bond is F, O, and N. All right, so the nitrogen can definitely hydrogen bond. So alanine is the one that cannot hydrogen bond. All right, there you go. All right. What quantity of NAG3 was required to reach the equivalence point in the titration? Okay, pretty simple here. Equivalence point for NAG3 is the one on the left. So this is a 1-to-1 molar ratio. All right. Okay, 1-to-1 molar ratio of lysozyme with NAG3. Okay, so in order to do this, they're asking for moles here. So in order to do this, we have to convert this into moles. And whatever that is in moles is going to be equal to NAG3. Okay, does that make sense? I'll do it out right here. Okay, so Hue lysozyme, they had 1 milliliter of a 0.1 millimolarity solution. Okay, so they had 1 milliliter, so 1 milliliter, all right, of a 0.1 millimolarity solution. Okay, I like to write it out like this first. So 0.1 millimolarity solution. Okay, and I don't like to write M for molarity. I like to write, instead in parentheses, moles per liter. Okay, I like to write the units out. And then I can see what cancels with what. So we're going to multiply this to make this easier. This is going to be 1 times 10 to the negative 3 liters. All right, times 0.1. This is 0.1 times 10 to the negative 3, which is going to be, all right, it's going to be 1 times 10. And because I moved it to the right due to Lars, I'm going to subtract. So 1 times 10 to the negative 4. Okay, moles per liter. And liter is going to cancel, and we get moles. Cool, we get moles. So 1 times 10 to the negative 7 moles. 1 times 10 to the negative 7 moles of lysozyme. All right, even though they're asking for the quantity of NAG3, okay, since we're a 1-to-1 molar ratio, all right, and since we're at the equivalence point, all right, the amount of moles of lysozyme is equal to the amount of moles of NAG3. So this is the equal to the NAG3. So this, they're, okay, nanomoles. This into nanomoles is what? So if I want this to be nano, this has to be -9. So I'm going to have to move which way? So Lars, I'm going to have to move to the right. So 1, 2 is going to subtract by 2. This is going to be 100 times 10 to the negative 9. So nanomoles. That's how you do it, guys. Let's keep going. What was the experimentally determined value of KNAG from the study described in the passage? All right, so they want KNAG. They want KNAG. All right, okay. All right, so when you see this, guys, you should immediately think y equals mx plus b. All right, so I'm going to screenshot this and bring it to, okay, bring it to the whiteboard here. Okay. Let's make it a little easier for you guys. Okay, so when you see this, think y equals mx plus b. All right, KNAG 3 over KAP is equal to the y. K nag times nag is mx. So K nag is m, the nag is x, and the plus 1 is plus the b. All right, so 1 equals b, x equals nag, k nag equals m, and y equals k nag 3 over k APP. M is the slope. M is the slope. So k nag is equal to m, which is equal to the slope. Okay, slope of what? Well, luckily they gave us this plot right here. Okay, and they told us the value of k nag could be determined. All right, so how do we find the slope of this? How do we find the slope? Go back to grade school. All right, rise over run. All right, so the rise at 2 different points and the run at 2 different points. Okay, so here's the first point and here is the second point. We could use any points really, but these are easier because this is just 2 and this is 1 here. All right, so I'm gonna use those points. So how much did it rise to go from here to here? Well, it rose 1 to 2, so it rose by a value of 1. Okay, it rose by a value of 1. And how much did it run? Run is to the right. So how much did it run from here to here? Well, it rose 1 and it ran from 0 to 0.02. So it ran 0.02 molarity. All right, so 0.02 here. Okay, and we divide 1 divided by 0.02. Now, all right, and for some reason my brain doesn't work like this, so I got to make it a little easier for me. So it's going to be 1 times 10 to the 0 over 2 times 10 to the negative 2. All right, I mean, for some reason this just works a lot easier for me. So 1 over 2 is 0.5. 0 minus negative 2 is going to be plus 2. And then move this to the right, you get 5 times 10 to the 1, which is equal to 50. All right, so 50, just like that. And we got it right, and we keep going. An ITC experiment is conducted by injecting compound 1 into a solution of protein A, giving large measured heats and a high affinity constant K1. Okay. A CITC experiment under identical conditions, but in the presence of 10 millimolarity compound 2, gives the same heat curve and KAPP equals K1. What change to the experimental conditions can result in measurable heat differences? And KAPP is less than K1. All right, so the K1 is the constant. It's the affinity constant. All right, this is compound 1 in a solution of protein A. It's giving large amounts of heat out, okay? And it has a high affinity constant. When we add compound 2 to this experiment, all right, when we add a concentration of 10 millimolarity of compound 2, what happens? We get the same amount of large heat, and we get that the KAPP equals K1. So the affinity is equal to the KAPP, the same thing. All right, the association constant is the same, and the amount of heat given off is the same, even though we added compound 2 to this experiment. All right, they want to know what to do so that we have differences in heat and the affinity constants change. All right. In order to have different amounts of heat, you're going to have to increase compound 2. So how did I know that? Well, this is in a CITC. Remember CITC was competition isothermal titration calorimetry. All right, this compound 2 is competing with compound 1, but compound 1 is winning. All right, when we add 10 millimolarity of compound 2, compound 1 still wins. We still get the same results as if it was just compound 1. So in order to stop that, we need compound 2 to win. If compound 2 wins, we're going to have different amounts of heat given off, and we're going to have different affinity. So how can we make compound 2 win? We make it win by adding more of compound 2. Okay, so dilute all the solutions. No, if we dilute all of them, we're still going to get the same amount. We're going to the same amount of compound 1 and the same amount of compound 2. Okay, and that's not going to help compound 2 win. Increase the concentration of compound 1 in both titrations. This would make compound 1 win. All right, we don't want compound 1 to win. If compound 1 wins, then we're going to have the same amount of heat being expelled in the same affinity. All right, increase the concentration of protein A in both titrations. If we increase the concentration of protein A, compound 1 is still going to win. All right, we're just making more, sites available to bind. That's it. All right. Increase the concentration of compound 2 in the second titration. Yes, if we increase this, compound 2 is going to win. We're going to have a different amount of heat. It could be more or less. It's going to be a different amount of heat being given off. And the affinity will change 100%. All right. So the answer for this one is D. And here's the explanation if you guys would like. And yeah, that's it for this video, guys. Hope you enjoyed. I was kind of distracted with this, not going to lie, with the construction and my dog barking. So I was a little over the place. Comment down below if you have any questions. I'll be more than happy to answer them. And I'll see you guys in the next video.